Let me remind you that we will have our tests on Wednesday. Test 1 is this Wednesday, July the 8th. And I will post the test at 11 o'clock. You need to turn in by 2. You need to stop working at 2 p.m. and submit it by 2:15, as I remember. Let me see the instruction. I believe you have seen the instruction for your for your test 1. I posted since the first day of class, I believe. Oh, that's not right. Yeah, you need to turn it in by 2 o'clock. No, submit it by 2 o'clock, not 2:15. By 2 o'clock. Now, the test itself, when I wrote the test, like what I said before many times, when I wrote the test, I have in mind that you will take 2.5 hours. Okay, 2.5 hours. That's why then I told you that your class time is 11:10 to 2 o'clock, right? That's your class time. But then in my instruction, I assume you will start working from 11:10 to 1:40. That's 2.5 hours. Okay, now then I posted at 11 o'clock because I assume you need extra time to write down some problems, or you need to print it out. And then the other 20 minutes up to 2 p.m. is for you to take the picture and then convert that to PDF and then post it on Canvas. Okay, that's why I give you such time. But keep in mind that you need to hit the submit button by 2 o'clock. Okay, and you need to stop working at 1:45 the latest. Okay, now that's for your test 1 this Wednesday. Make sure your printer is working. You know what to do. You already practiced from quiz 0 and quiz 1, 2, 3, I believe. Now let's start the lesson. Today we will go on, continue the last part of this 2.2 on reflection. There are 3 parts, reflection with respect to the y-axis, with respect to x-axis, and respect to the origin. Now let's observe the following thing. Suppose I pick a coordinate on the coordinate system. Let's say I pick this coordinate here, coordinate 4, 3. I have a chat. Let me see what's that. I have a question from quiz 1, 2, 3. Let me post the solution this afternoon, and then once you see the solution, then you take a look. Then you ask me a question. Is it okay? Yeah. Now let's say we have this point coordinates here. Now then, suppose we reflect this coordinate with respect to the y-axis. This is the y-axis. If I reflect this coordinate with respect to the y-axis, then the resulting coordinate will be the same y. Can you imagine if you reflect with respect to the y-axis, then the height will be the same, right? But the x will be -4 in this case, which is the opposite. Okay, so when 4, 3 being reflected with respect to y-axis, the result is the same y opposite x. when I reflect that with respect to the y, to the x-axis, notice that if I reflect that with respect to the x-axis, then it will have the same x, but the y will be the opposite. With respect to x-axis, it will be the same x, opposite y. Now, when we reflect that with respect to the origin, we will get -4, -3. If we reflect that with respect to origin, then you will get the opposite of x and the opposite of y. Okay, now you see that when we do reflection, we see the following situation, the following phenomena. That if I have coordinate x, y, reflected with respect to y-axis, the y will stay the same. The x becomes the opposite. With respect to the x-axis, the x will stay the same, the y will be the opposite. With respect to the origin, then we will take the opposite of x, the opposite of y. Okay, then I hope this picture actually help us to understand. Our textbook didn't go to this very basic view though. I go this far because, in my opinion, if once you can visualize and summarize, so you visualize the blue color first, and then you summarize this red color, then we can go on quite easily into the following situation. Suppose, for example, let line 1, line L, call that L1, be the equation, the line y equals to 2x minus 1. Then part A, find the equation of the line. Reflected by, with respect to y-axis. Now we know when we reflect with respect to the y-axis, the y will stay the same, the x will get the opposite. Okay, so I will copy the same equation here, but I replace the x by negative x. So y equals to 2 times negative x minus 1, which is y equals to negative 2x minus 1. Now let's take a look on my graphing paper, my graphing software, to confirm what we have. Y equals to 2x minus 1 looks like this. Now then, suppose I replace the x by negative x such that I get negative 2x minus 1. You see the reflection with respect to the y-axis. Right? Let me move it here. Okay. So if you reflect with respect to the y-axis, you replace the x by negative x, but then you keep the y. Now what happens if I reflect that with respect to part B? Find the reflection of the equation for the reflection of L1 with respect to x-axis. So that line, x-axis, let me call it that way, that will be replace the y by negative y, and the x stays the same. Okay, but I cannot have, that's not the slope-intercept form. In slope-intercept form, it will be negative of 2x minus 1, which will be y equals to negative 2x plus 1. Okay, let me quote you the picture. That's what it looks like. You see? Then you see that, for example, this guy becomes that guy, right? This guy, let's say I pick this one. Oh no, that's too far. Maybe this one here reflected to this, right? This guy reflected to that. Now the thing is, it applies to all coordinates, not only those two coordinates. So you see that when we reflect with respect to the x-axis, what you need to do is to replace the y by negative y. Now, similarly then, if I reflect with respect to the origin, then the equation of the line will be replace the y by negative y, replace the x by negative x. So y equals to 2x plus 1. Okay, now I apply these two lines so that you can imagine that easier. Okay, you can imagine that easier. But this actually applies to everything else. This applies to everything else. Let's say, for example, if I have let y equals to x squared minus 3x plus 4. Okay, call that curve 1. Find the equation of the curve, in this case it must be parabola, resulted from reflecting C1 with respect to, let's say, with respect to the origin. So you will see that the curve with respect to origin, that will reflect with respect to the origin, the y becomes negative y, the x becomes negative x. So I get negative y equals to x squared plus 3x plus 4. If I set y by itself, I get negative x squared minus 3x minus 4. Okay, that's the equation. Now, let's see if that's the case using my graphing software, just to confirm. Okay, so the next one is x squared. I think it's negative x squared. Negative x squared, not like that. Negative x squared, and then minus 3x minus 4. That's for the second one. The one after you reflect that. The one before you reflect was x squared minus 3x plus 4. Let's zoom it out. Do you see that? Let me put it into our node. You see the purple color, let me use green color. Okay, the purple, let's say this coordinate here, when you reflect that with respect to the origin, it gives you this one. Okay, the Y-intercept 0,4 that you originally have now becomes, when you reflect with respect to the origin, this is what you get, right? And so on and so forth. So I hope you see the procedure that what do we do if we do reflection? When we do reflection, with respect to x-axis, what happened, with respect to y-axis, what happens, so on and so forth. Now, that gives us one new thing though. Going back to transformation that we learned last Friday, then to reflect with respect to y-axis, what you do is you change the x, you replace x becomes negative x. To reflect with respect to x-axis, you reflect y becomes negative y. Okay, now that gives us a hint. Then, for example, what happened to the graph of y equals to negative absolute x plus 2 plus, let's say, 4. There are 3 transformations here. The first one, we start with absolute of x. We know the graph looks like this. Graph looks like this. Okay, and then from there, you move it 2 units to the left. And then applying negative to that, to the whole set. Yeah, it actually comes from this, y equals to absolute of, this one here, y equals to absolute of x plus 2. Now you replace the y by negative y. So I get y equals to negative absolute x plus 2, right? Now then, from what we know, replacing y by negative y will reflect the graph with respect to the x-axis. Then finally, y equals to negative absolute x plus 2 plus 4, we'll move that 4 units up. Okay, so that's the sketch. Now, let's see what if I sketch that in more detail. If I sketch that in more details, that will look like second. It will look like the following. The vertex was -2, upside down, up 4. Boom. That's the vertex. Okay. Now, supposed to be something looks like this, right? Originally, but because I make it upside down, becomes. Okay. So the better picture now becomes. The better picture now. Let me scroll. The better picture now becomes. That's the vertex. Pin this. Okay. That's the vertex, and we'll go this way. And this way. That's what the graph looks like. Okay, and this will be the axis of symmetry. Right? So it maintains the shape, but this time because we reflected with respect to the x-axis, it becomes upside down. Okay. Now through algebra, we will be able to find the x-axis, the y-axis, and from here we see the domain will be a real number as usual. The range will be -infinity up to 4, including 4. The y-intercept, you plug in x equals to 0. The function is y equals to absolute x plus 2 plus 4. So y is equal to negative of 0 plus 2 plus 4. That's y equals to -2 plus 4, which is true. So the y-intercept is 0, 2. And we confirm the y-intercept is 0, 2. Okay. Now how about x-intercept? We set the y equals to 0. Negative absolute x plus 2 plus 4. Move the absolute to the left-hand side to make it positive terms. So x plus 2 equals to 4, or x plus 2 equals to -4. X is 2, x is -6. So the x-intercept will be 2, 0, -6, 0. Which if we compare with the graph, 2, 0 is here, -6, 0 is here. Okay. And the axis of symmetry, x equals to vertex is -2, 4. Okay, let me write it down there. The vertex -2, 4. The axis of symmetry is x equals -2. Okay, now that's about this reflection. That is about this reflection. Our textbook doesn't have questions about this reflection with respect to x-axis or y-axis yet. Not yet at this time. But let's apply this into other functions. Yeah, in 2.4 we will talk about formally talk about functions. But before I get to 2.4, let me enrich you with 2 more functions whose basic shape is something I expect you to know. The third function, so important basic functions. The first one you already learned, y equals to absolute of x. The second one is y equals to x squared. We have learned those two. Now, the third one is y equals to square root of x. Okay. Now, you will see that for the y to be a real number, x has to be non-negative. You will see that will be the domain. Now, basically, the guy inside the radical for square root has to be non-negative. Okay, that's the domain. And as for the range, if you remember, square root means has to be at least 0. So you will also see that the range under square root will be at least 0, 2. Okay, now notice that this is actually the quote-unquote inverse, positive inverse of x squared. Now, what does it look like when we sketch the basic graph? When we sketch the basic graph for y equals to square root of x, notice that when I create a table, when y is 0, x is 0. When y is 1, the x is 1. The y is 2, the x is 4. Okay, so the coordinates are 0, 0, 1, 1, 4, 2, and actually the next one will be 9, 3. Here. Okay, so the graph will look like this. If I copy, it's not a line though, it's not a line. It's more into parabola, half of that parabola. Okay, now if I reflect that with respect to, if I reflect this with respect to the x-axis, then you will see the inverted parabola. Okay, this blue one is y equals to negative radical x. If you invert that upside down. Okay, now what you need to remember are these coordinates. Start from origin, okay, up 1, right 1, up 2, right 4. Okay, very similar to our square, very similar to our x squared situation. Very similar to our x squared situation where we have 1, 1, 0, 0, to the right 1, up 1, right 2, up 4, right? Okay, but this time when we invert that, then instead of right 1, up 1, it becomes up 1, right 1. Instead of right 2, up 4, we invert that to be up 2, right 4. Okay, so one of them looks like this, the other one looks like this. Okay, so the yellow one is for x squared, the blue one for square root of x. Now, what you need to remember is the basic graph of this square root, the red color one. That's the one you really need to know. Okay, now then suppose, for example, maybe I give you another one. That's for y equals to square root of x. Let's practice with this first. Let's practice with this first. Suppose we want, for example, sketch the graph y equals to negative square root of x minus x plus 4 plus 3. Now, don't try to do it with plotting one by one coordinate. No, that will take you too long. Maybe not too long for this question, but you know, we still have 4 or 5 weeks, like 5 weeks from now, right? I mean, I think I should say, yeah, 5 more weeks. Okay, so if every graph you do it that way, then you will spend too much time for unnecessary, insignificant coordinates. Instead, we will do it this way. We start with the basic graph, square root of x. That's why you need to know what it looks like. Okay, and then I will move it to the left 4 units. And then I reflect that with respect to the x-axis. And then I move up 4 units. 3 units. Okay, so originally, that's square root of x. I move 4 units to the left. So that's what it looks like. And then make it upside down. Comes like that. And then we move up 3 units. That's the new quote-unquote vertex now. So on. Okay, now let's put them in practice. So originally the quote-unquote vertex is here. The quote-unquote vertex is here. 4 units to the left, right? And then make it upside down. And then up 4 units. So the new vertex, I'm sorry, up 3 units. So the new vertex will be there. Okay, the new vertex will be there. Let me repeat it again. We start from square root of x. It looks like this. Now then I move 4 units to the left. Now it looks like this. Don't forget that the shape has to be the same. Okay, so this is y equals to square root of x. Now y equals to square root of x plus 4. Now then you make it upside down. Make it upside down. Now this is our y equals to negative square root of x plus 4. Then finally, we move it up 4 units. So the vertex originally negative 4, 0, now up 4, it's here. Now instead of up 1, right 1, now becomes, because of reflection with respect to x-axis, it becomes down 1, right 1. Down 2, right 4, down 3, right 9. Okay, now and then I sketch that. That's what the graph look like. Okay, now especially if you don't have graphing paper, then you need to give me these important coordinates, which are negative 4, 3, negative 3, 2, 0, 1, 5, 0. Okay, that's the coordinate. Now then, suppose I want to do some analysis on that. Y equals to negative square root of x plus 4 plus 3. What is the domain? From the picture, you can see the domain is from negative 4, including negative 4 to infinity. But the way we get that is really that the guy inside the house has to be greater or equals to 0. Has to be greater or equals to 0. So x is greater or equals to negative 4. Okay, that's how I get this thing here. Now, how about the range? Now, we know the range is originally from 0 to infinity, right? Maybe instead of doing here, let me do it, go back to here. Go back to here. You see the range will be supposed to be from 0 to infinity, right? Moving it 4 units to the left, keep the same range. But when we invert that upside down, the range becomes inverted also. That's the range will be negative infinity up to 0. Then when we move it up 3 units, we end up with the range negative infinity up to 3. So for you to be able to find the domain and range here, especially the range, you need to be able to imagine what the graph looks like. Okay, and then quote unquote vertex. It's not a vertex, but I call it quote unquote vertex. The place that you start with, you start graphing it with, that's negative 4, 3. How about the y-intercept? Just like before, to find y-intercept, you set the x to be 0. That's negative 2 plus 3, that's 1, 0. I'm sorry, 0, 1. That's y-intercept, 0, 1. And I believe we can confirm it here. This is the y-intercept here. Later on, when we do our algebra, you will find the x-intercept supposed to be 5, 0. Let's confirm that. For x-intercept, 0 equals to negative square root of x plus 4 plus 3. Now, that's why we learned to solve equation, radical equation last time, right? So we isolate the radical. The other side already positive, so I can square both sides safely without any doubt. So x equals 5. Now we confirm that the x-intercept is 5, 0. Now the fourth basic graph I need you to memorize. The fourth basic graph that I need you to memorize. So we have absolute of x, x squared, square root of x. Now the fourth one is y equals to 1 over x. Y equals to 1 over x. Now the graph looks like, let's do some table first. Notice that when x equals to 0, the y is undefined, right? So, so you see that the domain right away, that you see that the domain is all real number except 0. Okay, that's for the domain. When I plug in x equals to 1, I get the y is 1, x equals to 2, the y is 1/2, x equals to 3, I get 1/3. In fact, if I put 1/2 into the x, I get 2. I put 1/3 into the x, I get 3. Now let me plot these coordinates first. 1, 1, 2, 1/2, 3, 1/3, okay, and 1/2, 2, 1/3, 3. So if I connect the dots, it will be approximately something looks like this. Okay, now also notice that if I replace the y by negative y and x by negative x, it simplifies back to the original graph. Now, if you see this kind of phenomena, if you replace x by negative x, y and negative y at the same time, and it simplifies back to the original equation, it means it has origin symmetry. Y equals to 1 over x has origin symmetry. Okay, so 1, 1 becomes negative 1, negative 1. 2, 1/2 becomes negative 2, negative 1/2, and so on and so forth. Okay, so now we get, this is still part of the graph of y equals to 1 over x. Okay. Okay, so it actually looks like that. The graph of 1 over x looks like that. Now you will see the range for this. You can get any value of y except 0. Okay, now you need to memorize this 10 coordinates: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is basically 5 coordinates that you actually rotate or reflect with respect to origin. Okay, now then using that basic graph, for example, what will this look like? Y equals to negative 1 over x minus 2, let's say plus 3. How do we sketch that graph? How do we sketch that graph? Well, we will start with y equals to 1 over x, and then move it to the right 2 units. And move it to the right 2 units. It becomes like this, approximately. Right? Maybe I use another color. So it becomes like this. And then I reflect with respect to the x-axis. Equals to negative 1 over x minus 2. Means I reflect that with respect to the x-axis. So it becomes like this. Okay, and finally we move up 3 units. This is the coordinate system. Move 2 units to the right and move up 3 units. So the curve now becomes something that looks like this. Now let's sketch the graph. The new quote-unquote vertex is, 2, 3. Okay, and use helping lines to help us graph it later on. But this quote-unquote vertex is actually not part of the graph. Okay, it's not part of the graph. Okay, I just try to visualize that my quote-unquote new origin is there. Okay, now then the actual graph will be here, 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 here. union this guy here, 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 here. Okay, that's what the graph. Then, what is the domain? Let me rewrite the function, negative 1 over x plus 2, I'm sorry, x minus 2 plus 3. The domain will be all real numbers except 2. Right? Because if x equals to 2, it becomes undefined. Right? Which I can write in our notation, all real numbers except 2, or you can also write negative infinity up to 2 union 2 to infinity. As for the range, that will be all y where y cannot be 3. Now notice that originally it cannot be 0. The y cannot be 0. Right? Now because you move it up 3 units, then the y now cannot be 3. Okay, so there will be all real numbers except 3. Okay, you can try. If you plug in x equals to 3, you will get undefined. If you plug in the y equals to 3, you will get undefined. Subtract by 3 both sides, so I get 0 equals to negative 1 over x plus minus 2, right? Okay, and then I multiply by both sides by x minus 2, I will get 0 equals to negative 1, which is a contradiction, so no solution. No solution. In other words, no x such that y equals to 3. Because of that, because no x that gives you y equals to 3 means y equals to 3 is not in the range. Okay, now that's the later part of 2.2. Now, even though I call this 2.2, I actually already get into part of 2.5. If later on you see 2.5, if we go 2.5 later on, you will see that we learn transformation, reflection. The only thing that we have not done is the vertical or horizontal stretch or shrink. Okay, but that's the small part of that's the part of the big part of 2.5 actually, which I implicitly had covered when I did 2.2 here. Okay, now we did 2.3 last Friday. I will go on with 2.4 function. Definition of functions. Definition of function. Let me use a single S. A function f from, I think I prefer to say is a function is a correspondence from a set which we call domain to another set which we call range, such that each element in the domain corresponds to exactly one element in the range. Visually, suppose I have a domain and a range here. We call this mapping method to explain. So let's say this is the domain with elements A, B, C, and range here we have elements 1, 2. Now then the following is the mapping of a function. Each element in the domain corresponds to one element in the range. Okay, which if we try to use coordinate to express that, then this coordinate consists of two components. The first component is where it comes from in the domain, and A goes to 1, so the coordinate will be A, 1. B goes to 2, B, 2, and C, 2. You see, for every first component A, B, C, okay, it goes to exactly only one element in the range. Okay, now this is a function. Suppose if I add one more thing, B beside correspond to 2 also corresponds to 1. Then this is not a function anymore because you have an element in the domain, in this case is B, corresponds to two different elements in the range. So this is not a function anymore. It is still a relation, but it is not a function. Okay, so it's not in the function it's not a function anymore. Now, in the coordinate system, when you write it as a coordinate, what we had earlier was B going to 1. Now, from the coordinates, you see that if B goes to 2 and B also goes to 1, this guy is a cheater. Okay, B goes to 2, but B also goes to 1. It makes it not a function anymore. Okay, so if you have two initial starting points B, but it lands on 2 and 1 in the range, it makes it not a function anymore. Okay, now one of the big consequence about this, when we graph a function, it must satisfy vertical line test. Now, what is vertical line test? A vertical line test is the following. Every vertical line will intersect the graph of a function at most once. Now we will see this phenomena later on. After the break, we come back, we take a break, we come back at 12:15. Now, the notation we use up here, we usually call this a mapping method. Mapping, while this one here is coordinate. Can be used, by the way, or ordered pairs. Set. Can be used even if the relation is not a function. Okay, so even if the correspondence that we have are not functions, we still can use either one of these mapping or ordered pair set to describe the relation. Now, but only if it is a function, only if it is a function, we then can use fx notation. Okay, now for example, if you look at the ordered pairs that we have above there, okay, a goes to 1, we can write it as f of a, where a is the input, the output is 1. F of b, the input is b, the output is 2. F of c, if the input is c, then fc, the output is 2. Okay, that's what we have there. Now, again, only if it is a function that we can do so. Now, I believe you have seen these functions before. Okay, I just try to strengthen the conceptual foundation further, and especially under what situation we can use that F notation. Now, let's see, for example, number 4 in our textbook. It's section 2.4, number 4. Let fx equals to x over x minus 3. So if the input is x, the output is this. Now we see that the domain of this function is, the domain of this function is all real numbers except 3. In other words, when I plug in x equals to 3, if I plug in x equals to 3, the output will be undefined. Okay, now what happens if I plug in x equals to 2 or negative 2? F negative 2 means I replace the x by negative 2 and then compute it from there. 2 over negative 5, which is 2 over 5. Okay, now this notation means that coordinate negative 2 comma 2 over 5 is on the graph, right? Okay, well, because the input negative 2 give us output 2 over 5. Okay, how about f0? When we plug in x equals to 0, I will get 0 over 0 minus 3. That is 0 over negative 3, that is 0. So the coordinate correspond to that statement is when input is 0, the output also 0 is on the graph. Which, if you think about it, by the way, that happens to be the x-intercept and also the y-intercept, right? That's the x-intercept, which is also y-intercept. Let's say this is the y-intercept, and when I need to find the x-intercept, to find x-intercept, I set the y equals to 0, and then multiply both sides by the LCD, I get x equals to 0. So the x-intercept is also 0, 0. Okay. In chapter 4, I believe, we will learn to find the range of this function in more accurate way. Yeah, we will learn the range of this function in more accurate way. For now, we can answer the issue of domain already. To find the range, I will show you how to do that, I think in 2.7. Yeah, in 2.7, which is part of your test tool. We will talk a lot more about 2.7. Maybe not, maybe not. That will be chapter 4. Not now, not now. Okay, now that's about find the value of a function at certain x value. Now let's go on to, for example, number 8. Number 8, let fx equals to 3 minus x squared. 3 minus x squared. And we will want to find this part A. What is fa? Part B, what is f negative a? Part C, negative fa. Part D, f of a plus h. Part E, f a plus f h. And part F, this is an important one, f a plus h minus f a over h. This is very important, especially when at the beginning of your calculus later on. This expression is very, very important. Okay, but for now, let's review on the notation. Okay, let's see part A. If fx equals to 3 minus x squared, then fa will be 3 minus replacing x by a, right? This is the furthest I can go. Part B, what is negative fa? Negative fa is, I'm sorry, part B is f negative a. F negative a. So I replace the x by negative a, right? Replacing this x here by negative a. Okay. Negative a squared is 3 minus a squared. Oh, by the way, so from here you notice that when I replace x by negative x, let me use another color. When I replace x by negative x, I get the same function as the one we had originally. Right? We have the same function as the one we had originally. Then this function has y-axis symmetry. This function has y-axis symmetry? Well, because replacing x by negative x gives the same function. But replacing x by negative x is basically reflecting that the graph of that function with respect to the y-axis, right? So I believe the graph of this 3 minus x squared looks like this. Right? Now then when you reflect this, when you reflect this part here with respect to the y-axis, it will become here. While the one on the left-hand side, when you reflect this with respect to the y-axis, it goes there. So you get exactly the same function when you reflect it. Now, with that, once you have that phenomena, then we say the function has, the graph of the function has y-axis symmetry. Okay, that will enable us to graph this a lot faster. Part C, about negative FA. This is if we try to reflect it with respect to y-axis. Okay, negative of 3 minus a squared, that's negative 3 plus a squared. No, they are not the same, so no, it doesn't have y-axis, doesn't have x-axis symmetry. Okay, it still have y-axis symmetry, but not x-axis symmetry. Part D, what does f of a plus h means? Again, I will replace the x by a plus h. So I get 3 minus a plus h squared. Foil that, I get a squared plus 2ah plus h squared, which will give me 3 minus a squared minus 2ah plus h squared. Now compare that with part E. What will FA plus FH means? FA means 3 minus a squared. FH means 3 minus h squared, which when I put together, I get 6 minus a squared minus h squared. I'm sorry, the one here should be minus here, not this, because I distribute the negative, right? Now, then from part D and E, you notice that FA plus H is not equal to FA plus H. Okay? We cannot just split it. We cannot just see that function as a distribution. No, we cannot. Okay, we cannot. Now then, how about part H? Part F. Part F, F A plus H minus F A over H. What's that? Now, the top left, this guy here, is something we have done in part D. Right? Let me just copy the result. That is 3 minus a squared minus 2ah minus h squared minus fa itself is 3 minus a squared over h. And from there, I simplify. Okay. This expression that we have on the left-hand side here, this expression here, is known to be difference quotient of the function at a. Now, don't worry about that right now. In a couple of minutes, we'll get into that. Maybe in 15, 20 minutes from now, or maybe half an hour, we'll get into that. Okay, but that's an important expression that you will need to see in calculus. Okay, let's simplify this. Let me slow down a little bit. Actually, at this level, I do expect you to be able to see that you can cancel the 3 and the a squared, right? Okay, I expect you to be able to see that. But suppose you don't, and I distribute, open the parentheses first, right? And then when you combine like terms, you will get negative 2ah minus h squared over h. I can factor the h out. Actually, I can factor negative h out. I get 2a plus h over h and cancel the h. Okay. How far do you want us to simplify, Thomas? I will tell you the key later on when it comes to dealing with this difference quotient. I will tell you the key later on in how to get this difference quotient. Now let's go back to the graph first. Go back to the book. I would like you to take a look, compare question number 15, question or problem number 15 and number 16. 15, number 16. They give you the graph there. Okay, they give you the graph there. And by the graph only, by looking at the graph only, can you tell if that's the graph of a function? Now, once you're done with that, while I try to quote that from the textbook, I would like you to also take a look on number 18. On number 18, they give you the graph. And you need to find the domain and the range of that graph. Okay, let me quote it here. How do we know if number 15, for example, is the graph of a function? Or if not, why? How do we know those? For number 15, don't forget, once you are given a graph, okay, you can check right away if, actually you can just do it visually, that if it is a function or not, what you can do is you draw a random vertical line. A random vertical line. As long as that vertical line intersects the graph at most once, then it is a function. Okay, so for number 15, it is the graph of a function because it satisfies vertical line test. Every vertical line will intersect the graph at most once. Now, number 16, however, is not a function. It is not the graph of a function. Because now, then find a counterexample. Find a line, a vertical line that intersect the graph at most once. Let's say this one here. Actually, I'm thinking too hard, right? You can just look at the Y-intercept, right? Okay, because there is a vertical line intersecting the graph at more than one point. In fact, what we have here, it intersects at 3 different places. Right? Not to say that if you look at the Y-intercept, it has 3 Y-intercept too, right? Then right away, it's not the graph of a function. Okay, that's for number 15 and 16. Now, what happened if we do number 18? Let me get that first. Get the graph first. Number 18. We have this graph here. What's the domain? Number 18, what's the domain? The domain is all the axes that has a coordinate. So you see that this -4, 3 here. So you have x equals to -4 all the way to this coordinate here, right? The x is -2. Okay, so the domain for that part is including -4 up to -2. And then union, I continue with this part here. Okay, this part here, it's open circle. So it's from -2 up to -2 up to 4, not including the endpoints. Okay. Up to 4, not including the endpoints. Now the thing is, notice that this actually suit together. I mean, they're connected, right? They are connected, such that we can sew them together, put them together, becomes -4 up to 4, not including 4 though. Okay, that's the domain. How about the range? Now, for the range, you look at the y. For the range, we look at the y. For the range, we look at the y. The y starts from -3, right? Starts from -3, not including -3 because it's open circle here. Up to -1, not including -1 because it's open circle. So -3 up to -1. And then we continue from 1 up to 3, including 1, including 3. So including 1, up to including 3. That will be the range. Okay, that's for this number 18. Let's do one more problem, but this time we will see more. Number 20. Number 20, I will give you the graph later on, but the questions we need to answer, I assume you have the book, so you can start working on that. Find the domain for that number 20. Find the range. Find F1. And part D, find all x such that fx equals to 1. And part E, find all x such that fx is greater than 1. Okay, I will quote the graph very soon, but you can start working on that problem now. Now, let's see, what do you have for part A? What's the domain? For all, find all the x's that give you the graph. So we start from here, that's for the x, right? From here, go all the way, seems like it never ends, go all the way to 7, including endpoint 7. So the domain will be from -5 up to 7. That's for the domain. The range is all the possible y's. What are the value of y's we can get in that graph? The value of the y's, I think the minimum is -1. It goes up all the way to here, right? This is the minimum. That's the maximum. So it's from -1 up to 2. From -1 up to 2. So the range is from -1, including -1, up to 2. Now part C, more into your ability to read the graph. What is F1? From what we see here, when x equals to 1, the y is, the corresponding coordinate is negative 1 comma negative 1, right? So when x is negative, if x is 1, the y is negative 1. Okay, so you see from the graph, coordinate (1, negative 1) is where we find that answer. Then part D, find all x such that fx equals to 1. How do we do this? You draw a line, y equals to 1. I want to use this color. You draw the line y equals to 1. This is y equals to 1, right? And see what are the axes where this y equals to 1 line intersect that curve. You see they intersect here, right, for y equals to 1. Okay, now then from there you see that the axes are x equals to negative 3, x equals to negative 1, x equals to 3, x equals to 5. Here's the correspondence. Okay. Those are all the axes such that fx equals to 1. Now, then we go further and find x such that fx is greater than 1. You need to find all the axes such that you want to find all the axes such that when you plug in those axes, you get the portion of the graph above y equals to 1. So it refers to this part here. Refers to this part. Now, for those yellow shaded part, what are the axes? What are the axes? Now, the axis refers to from here to here, right? And then from here to here. Now, the thing is, do we include the endpoints? We will include the endpoints if there were an equal sign here. Okay, but no, here we don't include the endpoints. Okay, we don't include the endpoints because we don't include fx equals to 1, right? So in interval notation, that will be from negative 3 to negative 1 union, from 3 to 5. Okay, now that's for reading the graph. Next, implied domain. Or simply the domain. Suppose we are given a function. Suppose we are given a function. Can we tell the domain? Of course, most of the time, not by looking at that. We need to do something. But knowing those basic functions that I showed you before enable us to figure out the domain when we modify the question a little bit. For example, number 22. We have fx equals to square root of 4 minus 3x. the domain of a square root is this guy here has to be greater equals to 0. 4 minus 3x should be greater equals to 0. Okay, and then solving it, divided by 3, so x is less than equals to 4/3. So the domain is in interval notation because it is inequality. If I don't tell you anything, then the interval solution should be written in interval notation. That would be negative infinity up to 4/3. Okay, that's for number 22. Okay, now, by the way, let's see, I believe that's one of the question in your homework that you need to turn in. What's that? Quiz 1, 2, 3. Let me see the question. The last question requires you to know something. Okay, yeah, number 10. Find the domain of this. Find the domain of this. So Thomas, don't you think it's not fair that you didn't teach us square root, but you already asked that in your quiz? It's fair enough because I give you the foundation already. That for square root to work, then the guy inside the house, inside the square root, has to be non-negative. So x squared minus 5x plus 4 over x plus 3 has to be at least 0. That's what you need to solve. Now then, how do we proceed from here? Let's start at the top first. And because this is a non-linear inequality, then I need to go through the 3 steps process. And no other way, no other way. I want it this way. I want it this way. You have to do it this way. The only time you don't do it this way is when you don't follow my lecture. And trust me, you will get it wrong anyway. You will get it wrong. If you get it right this time, you will get it wrong eventually. Okay, so don't worry. Until you do it my way, you will always get it. You will get it wrong. And you get it wrong because of your procedure. So that's why even if you get the right answer but wrong procedure, I still mark you wrong. I penalize you by big time. Okay, I penalize you by big time. If your procedure is wrong, then it's just about time you get it wrong. If your procedure is right, then it's just about time you will get it right. Okay, now the critical numbers are x equals to 4, x equals to 1. Those are the zeros. Those are the axes that make it equals to 0. And x equals to -3 is the x that make it undefined. Sign graph. X equals to -3, 1, 4. The 1 and 4 are the zeros. And -3 gives us undefined. Now, and then when I test x equals to 0, when x equals to 0, I get negative and then negative and then positive. So this is positive here. Now, I can tell you the shortcut right now. If this is the first time you take this class, then there's something called the exponent. You look at the exponent of this critical factor. You see, the exponent are invisible 1, right? The exponent is invisible 1. Okay, so let me say it this way. Now, if the exponents gives is if the exponent is odd, then the sign to the left and right of the critical number is different, is opposite. If the exponent is even, then that will be the sign, the same. If, say, if exponent is even, then same sign to the left and to the right. I'll show you a fast example later on. But for now, because 1, x minus 1, the one here, the exponent is 1, right? So the sign has to be opposite on the other side of that 1. Now for 4, x minus 4, the exponent also 1, which is odd. So the other side of that 4 must have opposite sign also. Opposite of that negative, so this is positive. For the same reason, this is negative. Okay, because the exponent of x plus 3 is an odd number, so the sign here are opposite. The sign here, because 1 is a 0 with odd multiplicity, odd exponent, and change the sign, Now let me finish this question. So the solution, I need greater or equals to 0, means positive or 0. So the domain will be from -3 to 1 union 4 to infinity. Suppose, for example, this is kind of like review a little bit, but using a newer technique. Solve x minus 3 squared x plus 2 over x plus 4 to the power of 6. And I want this to be greater or equals to 0. Let's say I have something like that. Then the solution, it's already factored, so I can start with critical numbers. Factor and the other side is 0. X equals to 3, x equals to -2, x equals to -4. Sine graph. -4, -2, 3. X equals 3 give us 0, x equals to -2 also 0, x equals to -4 give us undefined. So then let me check y-intercept when x equals to 0. I'll get positive, positive. So that's positive. Now then, for critical number x equals to 3, for critical number x equals to 3, the corresponding factor is x minus 3, whose exponent is 2. Because the exponent is 2, then the sign does not change. The sign to the left and to the right of that critical number coming from a factor with even exponent will have the same sign. Now, x equals to negative 2 comes from a factor x plus 2 with odd exponent, invisible 1, right? Odd exponent, invisible 1, such that the sign here will change. There must be opposite sign. And negative 4 as a critical number comes from x plus 4 with even exponent, such that the plus minus sign to the left and to the right will not change. Okay, so the solution for this will be so I need positive and 0, huh? So that will be negative 2 up to 3 union 3 with infinity, or I can just put them together. That's from negative 2 to infinity. Boom. Couple more examples before I go on. Number 28. Find the domain of fx equals to square root of 4x minus 3 over x squared minus 4. So first one, 4x minus 3 has to be greater equals to 0 because it is inside the radical. 4x minus 3 has to be greater equals to 0. Now, if that were in the denominator, then it cannot be 0. Okay, it has to be strictly positive. But this is in the numerator on the top anyway, so it's okay to be 0. Okay, but at the same time, the denominator cannot be 0. So let's solve this. This is 4x greater equals to 3. X has to be at least 3/4. At the same time, x plus 2, x minus 2 cannot be 0. So x cannot be negative 2. X cannot be 2. Now, what will that be in interval notation? First, it has to be greater equals to 3/4. Right? So it is okay to have from 3/4 all the way to the right, except that I need to avoid x equals to negative 2 and x equals to 2. I need to avoid x equals to negative 2, which is not in the first, the purple interval anyway. So I don't worry about that, but it cannot be 2. Now, from there we say, so the solution will be, the domain will be from 3/4 up to 2, not including 2, and then you continue again, 2 to infinity. After the break, I will do the last but important part of that, this 2.4, something called difference quotient. Let's take a break. We come back at 1:16. Right now 1:06. We come back at 1:16. Okay, let's continue again. Difference quotient. Definition. I will tell you first what it is, and the interpretation is something I will do tomorrow. Okay. The difference quotient of fx, the function fx, denoted by dq subscript f, is given by dqf equals to f of x plus h minus fx over h. Okay, that's the difference quotient. Now, because this is so important in your calculus class later on, you will see that I always ask this question in my, at least in my test one. Okay, now I will provide you this formula all the time. When I ask you difference quotient, then I will always give you this formula. But once you go to go to calculus, you have to memorize it though. Okay, and then that's the formula. Then how do you apply that? Then simplify as much as possible until if we plug in x equals 0, if we replace h by 0, then we don't get 0 over 0. Okay, so basically, how do we know we can stop? We can stop when, if you physically replace h by 0, you don't get 0 over 0. Okay, let's see, for example. Let's see, for example, the easy one first. How about fx equals to my favorite linear function, 2x minus 1. Find the difference quotient. So find difference quotient of then solution. Let me find fx plus h first. This part here. Okay, let's get that one first. That is 2 times x plus h minus 1. That is 2x plus 2h minus 1. Now then, if you want to skip this one and just go ahead to difference quotient right away, go for it. But usually it gets a bit longer if you do so. So difference quotient will be the yellow part minus the blue part. Okay, so that will be 2x plus 2h minus 1 minus 2x minus 1 over h. Then you will see the 2x cancels, the 1 also cancel, right? So I get 2h over h. Now then, how do we know we can or cannot stop here? Now, you visually do this. If you replace h by 0, what you get? 0 over 0, right? Okay, so no, you cannot stop there. You have to go on. I will cancel the h. I get 2. Now, that's the easy part, though. That's the easy part. Let's see the slightly harder one, or if not a lot harder. Suppose I do the quadratic function, let's say. For example, fx equals to 2x squared minus 3x minus 4. I randomly pick a function, by the way, pick quadratic function. Then find the difference quotient. Solution. What I would like to do first is to simplify the yellow part first. Simplify this yellow part first. The first term on the numerator. That is 2 times x plus h squared minus 3 times x plus h minus 4. Now, a student brought it up to me that today is the last day to drop the class without W, and that student asked me if I can finish grading the quiz 1, 2, 3, I believe, so that he or she can decide to drop the class and avoid the W, or to keep on going with the class. Now, that's something you guys need to, I should say you guys, you girls, need to decide on your own, okay? Yeah, but of course I will try to give my best, my best professional opinion. But the things that you need to keep in mind is this: some of you actually started the class a bit late. Well, we start this class on the second week of this summer, and then the department chair allowed me to add students until Friday, basically. Okay, so that's what I did. So some students actually add the class very, very late. I think 2 of you had added on Thursday, and the other 2 actually added on Friday. So those people, especially those added on Thursday and Friday, I expect them to have hard time to actually catch up and finish the quiz 1, 2, 3 today. Okay, now if you have that issue, then you need to ask yourself the following situation. First, do you think you fit with my teaching style? Second, is it because if you don't do well with your quiz, is it because of you at the class late, but you believe you can catch up in 2 days, okay? Because I don't mind you not doing well with your quiz, but you need to do well in your test 1. I don't forgive you for that one, okay? If your test 1 is not good, I will say that, you know what, consider taking the Math 20, okay, intermediate algebra. But if you think it's because of you added the class late, but you believe you can catch up, then you should be fine. If it is because of your weak or lack of strong foundation, I so strongly suggest you to go back to Math 20. Okay. Now, my purpose here is not that I don't want students. I don't think I have enough students in this class, so your class will not making me busy when I grade it. Okay, so don't worry about it. Okay, I have no issue with more students in this class, but my issue is this: like if you are not doing well even right now, you may wonder if it is possible for you to transfer right now in this summer, transfer to Math 20, where you can fix your foundation better. Okay, this is the end of actually the beginning of the 3rd week. But when you ask for transfer, try to contact the department chair and say that you are already in pre-calculus, but I feel that I'm not doing well. I think my foundation is weak. I wonder if I can transfer to Math 20. Okay, that's what you will say. Now, but don't drop the class yet. Oh, no. You may drop the class, but But talk to the department chair that way. Who knows, she can help you get into a Math 20 this semester. Okay, hopefully that you don't spend too much time engaging in a class that you don't have foundation with in my class, but you can move to a class in which you can follow much better and provide you a better foundation the next time you take pre-calculus. Okay, so please don't take it as if I don't want students. I want students to drop a class. No, that's not my purpose. My interest is you can transfer as fast as possible with good grade. Okay, and for that to happen, you may need to fix your foundation first and then just perform very well since then, instead of keep on repeating the same classes and collecting F or C's or W. No, that's I believe that's not your interest. Okay, so act in your best of interest, but of course at the same time be reasonable to yourself, especially if you at this class late. Okay, let me continue from here. I will FOIL this guy. And I will distribute this. Okay, let me just distribute this further. This is equal to 4hx plus 2h squared minus 3x minus 3h minus 4. The reason I try to do the f of x plus h outside of that formula, outside of this difference quotient formula, is because I want to focus on the expansion of that term first. And there's a tendency that the top left becomes quite long. Maybe this one minus the blue part, the top right. Now I use this coloring so that you can kind of like keep track of what we do. Okay, on the top left here, this is 2x squared plus 4hx plus 2h squared minus 3x minus 3h minus 4 minus the fx, which is 2x squared minus 3x minus 4. You will see that, let me use a thin color, you will see that this guy, you will see that this guy cancel this, right? And then this guy cancel this guy cancel that, such that we are left with, on the numerator, we only have 4hx plus 2h squared minus 3h over h. Now I can factor the h on the top. I get 4x plus 2h minus 3 over h. Remember earlier I said that how do we know we can stop there? Well, try plugging x equals to 0. If you get 0 over 0 means you need to go on. You need to simplify further. Okay, which I do here. Then I get 4x plus 2h minus 3. Now, at this point, when you plug in h equals to 0, if you plug in h equals to 0, this part becomes 0, but you still have 4x minus 3, right? It means you can now stop here. Okay. A couple more problems. Maybe this is how important it is, such that I want to do more. A lot of them actually algebraic manipulation. Example 3. Example 3. Let's say we want to find number 50. Difference quotient of 1 over x squared. this will be, let me see this one first. Solution. Let's see what happened to f of x plus h. I will not FOIL this though. I will just leave it like this for now. The reason is because when I start working on difference quotient of that function, on the top left, I have 1 over x plus h squared. On the top right, I get 1 over x squared. Over h. Now, this is a complex fractions. This is a complex fractions. Now, on Thursday, I believe we learned how to tackle complex fractions, at which we multiply the top and the bottom of that complex fractions by the LCD. I remember I said that's actually the fastest method to simplify complex fractions. So then, if I multiply by the LCD, I think the bottom is okay. That will be h x squared x plus h squared. Right now, now I hope you understand. I didn't FOIL this part here because then I can see the LCD a lot better. Once I FOIL it, I don't think you can see the LCD faster. Then when I multiply by the LCD there, I will get x squared in the first term. So this guy times this, x plus h being squared cancel, right? Okay, I only have x squared times 1, that's x squared. Minus, now the second term, the blue part here, when I multiply by the LCD, the x squared cancel, I have x plus h being squared. Oh, Thomas, can I stop here? Let's see, if my h equals to 0, I get x squared minus h squared over 0, right? That's 0 over 0. No. It means I cannot stop here. I cannot stop here. Boom. Erase. What I will do is then I will FOIL the second term on the numerator. And I believe you can see something actually gets canceled. Right? You can open the parentheses first and then combine like terms. But you will eventually see 2hx minus h squared over x squared x plus h squared. Factor the h. Which will cancel with the h on the denominator. So the difference quotient of this function is 2x minus h over x squared x plus h being squared. Okay, notice that I know I can stop there because when h equals to 0, when I set my h equals to 0, I get 2x over x squared times x squared, which is not 0 over 0. Right? It's not 0 over 0. Okay, so I can stop there. Okay, that's how we know we can stop there. What happens if we have square root? Let's say if the function fx equals to square root of, let's say, x plus 4. Then the difference quotient is, well, f of x plus h first is square root of x plus h plus 4, such that the difference quotient is on the top left square root of x plus h plus 4 minus square root of x plus 4 over h. Now we cannot stop here because remember, when I make my h equals to 0, when my h equals to 0, I will get square root of x plus 4 minus square root of x plus 4 over h over 0, right? That's 0 over 0. Now I cannot stop there. Okay, I cannot stop there. I need to simplify. But the problem is, how do we simplify this? To simplify this, we multiply by the conjugate. Square root of x plus h plus 4 plus square root of x plus 4. Now you will see that in this case, our final answer have radical at the bottom, but that's okay. That's okay. For difference quotient, it is okay to have radical at the bottom, as long as when h becomes 0, it doesn't give us 0 over 0. Okay, now the purpose we multiply by the LCD so that we can invoke, we can use difference of squares for the numerator. We get x plus h plus 4 on the numerator minus x plus 4 on the top left or top right, and then at the bottom we get h times the square root of x plus h plus 4 plus square root of x plus 4. As you can see, x cancels, 4 also cancels, right? Such that we have only h on the top that will cancel with that h at the bottom. Okay, finally I will get 1 over square root of x plus h plus 4 plus square root of x plus 4. And we can see when h equals to 0, when h equals 0, I will have 1 over something, right? When h equals 0, I will get 1 over something, so I can stop here. Okay, now suggested homework from here will be suggested homework from 2.4 will be number 3, number 1, number 3, those are the Mickey Mouse one, number 9, number 11 and 13. I try not to give you too much, but I think these are quite short. 17, 19, 21 to 31, then 47, 49, 51. I think that's all you need to know. I think that's all you need to know from this 2.4. In 2.5, we learn, that's actually a big section, but I did most of them already. In this 2.5, we learn basic functions and then the transformation. So this is graphs of function. 2.5, that's graphs of functions. Later on, we will talk about, the first topic will be about even and odd functions. And then part B is about transformation. At which we have done most of them. Transformations, there are actually 4 types of transformations. There are 4 types of transformation. The first one is translation. We move the graph to the left or to the right, translation. And then the second one is reflection. We reflect with respect to x-axis, y-axis, or origin. Maybe I say that's a left-right translation, up-down. This is reflection with respect to y-axis, reflection with respect to the x-axis, or rotation with respect to origin. And then the third one is on stretch or shrink. Usually we call that dilation. You dilate it. Now that's what we will learn today from this section. And basically in the last 15 minutes, we will learn only this one. The last one, rotation, is something we will not learn in this course. I believe rotation is something you learn in Calculus 2 or Calculus 3 or linear algebra. Okay, so we will not learn this. Don't worry about that rotation. Okay, we will do only, we did translation and reflection already. We will do only stretch or shrink. And even in this case, I will only teach you, for now, I will only teach you vertical stretch or shrink. Now, I will start with this. I will go to example right away. I will start with, for example, how about y equals to 2 times absolute of x. So the basic function is absolute of x. That's the basic function. And then I stretch that vertically by a factor of 2. So you will see that gx, a new function, is constant multiple of that function. If you see something like that, it means this is vertical stretch by C. Let me graph it first so that you can really see what I meant. Okay, I'll start with the graphing. Give me a second. I need to grab my graph. It's actually not too hard, but you just need to focus and have good foundation in that what we have learned before, especially the translation. Move left, right, up, down, reflection. Right now, then we do the stretch now. Okay, now I will start with absolute of x. Okay, y equals to absolute of x. The graph looks like this: 0, 0, 1, 1, 2, 2, 3, 3, and on. Negative 1, 1, negative 2, 2, negative 3, and on. So the graph is approximately, this is just a sketch. Okay. It's approximately like this. Okay. Now, what is the effect of these two in front of that absolute of y? If I do the table, notice that when I do the table, if x equals 0, this is 0, this is 0. When x equals to 1, absolute of x is 1. 2 absolute of x will be 2. Basically, you see that I double the y value of the original absolute of x. If this is 2, the absolute of 2 is 2, and then I double it, becomes 4. Likewise, when I plug in, let's say, negative 3, right? X equals to negative 3, then absolute x is 3. And when I double it, it becomes 6. Okay, so what will happen is, whatever the y that you have in red, now you double it. 1 becomes 2, the y of 2 becomes 4, the y of 3 becomes 6. The y of 1 becomes 2, the y of 2 becomes 4, the y of 3 becomes 6. So the resulting graph, after you multiply it by 2, will look like this. And the other one will look like this. Okay. So you imagine this red one here, this red curve here, you kind of like stretch that. You stretch that vertically by doubling, because of this tool, by doubling whatever the y you have in red, you double it becomes, then it becomes stretched to the blue color. Okay, that's what you mean by a vertical stretch. Of course, if that tool, you replace that tool becomes, let's say, 1/2, then instead of stretching it, becomes taller, you make it shrink that, becomes shorter. Okay, give me a second. So let's experiment with this. I know this is quite complicated, but some students found it to be fun. So I hope you can find some fun here. Okay, so let's say I have y equals to negative 1/2 absolute of x minus 3 plus, let's say, plus 2. There are actually 3 movements. 1, 2, 3, 4. There are actually 4 movements here. Yeah, the first one, of course, we start with y equals to absolute of x, right? And then we move 3 units to the right. And then I shrink that by a factor of 1/2. I shrink that by a factor of 1/2. And then I flip that upside down. And finally, I move up 2 units. So that's order of transformations. But you start with that basic function, okay? Absolute of x. I move 3 units to the right. So the one here, the graph will be 3 units to the right. Okay, now what this 1/2 doing, is you shrink the y by factor of 1/2. So instead of moving up 1 unit every time you move to the right, now you becomes moving up 1/2 instead. Moving 1/2 instead. Okay, then what happened here? Then you flip that upside down. So it will be like this later on, right? And then you move up 2 units. Okay, now let's practice. Let's see in detail what happened, what we have at the end. So I move, it looks like this, right? Originally, that's absolute of x. Okay, move 3 units to the right. Okay, and then I shrink by 1/2. So 1 becomes 1/2, 2 becomes 1, 3 becomes 3/2, 4 becomes 2. Approximately, that's what it looks like for now. This blue one here is y equals to 1/2 absolute x minus 3. We are not done yet, though. We are not done yet. Next, we will flip that upside down, right? We will flip that upside down. So this blue on the right-hand side here will becomes here. Will become here. Before I move it up 3 units. Oh no, in this case, I move it up 2 units. Okay, so let me mark it first. This is y equals to absolute of x. This is y equals to absolute x minus 3. I think those two are okay. And the blue one, the shrinking, is the one that you need to pay more attention. Okay, and the upside down. So this is y equals to negative 1/2 x minus 3. Notice that the vertex is still 3, 0 though. The vertex is still 3, 0. Now, then in your test or in your quiz, you don't need to show this. Don't need to show. Don't need to show. Okay, I show it to you here so that you know how I get my final answer. Okay, yeah, but then what you need to show me is this one. This is what you need to show. Show this. Okay. So what happened was the last one we have is the green one, but that's before we move up 2 units, right? So from that 3, 0, I move up 2 units, and the slope is it's right one, down half, 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 down half. These are the coordinates I will have. Okay, I do the sketch first. Now let me do the graphic. That's what the graph looks like. Okay, so if we analyze this further, y equals to -1/2 absolute x plus 3 plus 2. What's the domain? It's all real numbers, no question about it. How about the range? -infinity up to 2, right? Part C, how about the axis of symmetry? X equals to -3. Axis of symmetry is a line. That's a vertical line. That's, in this case, this is the axis of symmetry. So axis of symmetry should always be given in form of the equation of a line. The vertex will be negative. I think I copied this wrong. It should be.
Shouldn't the axis of symmetry be x equals 3? Or...
Should be x equals 3 because I copied this wrong.
Okay.
Yeah, I copied this wrong. That's why I make mistake there.
Okay.
Yeah, so it should be x equals 3. That's right. Okay, and then the vertex therefore is 3, 2. Okay, now then how about the y-intercept? The same procedure. The y-intercept, you set the x equals to 0. 0 minus 3 plus 2. That's -1/2 times 3 plus 2. That's -3/2 plus 4/2. That's 1/2. So the y-intercept is 0, 1/2. And you can confirm that in your graph here. Right? You can confirm in the graph that the y-intercept here is this. Right? You see that? And how about the x-intercept? X-intercept for the part F, you set the y equals to 0. And then solve for the x. Let me move the negative term to the other side, becomes positive term. Multiply both sides by 2. Now I have the absolute value isolated. Either x equals to 7 or x minus 3, x minus 3 equals to -4, so x equals to -1. So the x-intercepts are 7, 0, -1,0. Okay, so you see my -1, and 7, 0. Right? Okay. Now, tomorrow. Oh, you know what? I'm sorry. Let me. Yeah, tomorrow we will apply this into quadratic. Okay. Yeah. So 2.6 tomorrow, basically the application of what we learned in this 2.5 here. Now, about even and odd function. Even function. A function is even is an even function if it has y-axis symmetry. Therefore, to show that a function is even function, you need to show that when you replace x by -x, you get fx. Okay? That's what you need to show. Now, how about odd function? A function is an odd function if is an odd function if it has origin symmetry. So to show that a function has origin symmetry, what you need to show, or therefore as an odd function, you need to show that f negative x equals to negative fx. Okay, now I assume you have your textbook with you. The work is actually quite simple, so I would like you to take a look yourself on example 1. Example 1 in our textbook. Section 2.5. Okay. Tomorrow I will do a little problem from here, but just to confirm that you have it. Okay, but for this 2.5, your suggested homework will be, for this 2.5, your suggested homework will be 3, 5, 7, 9. Now, a function may be even, a function may be odd, a function may be neither. Okay, as long as it satisfies this, you call that even. If it satisfies this, you call that odd. If it doesn't satisfy any one of those, then you call that neither. Okay, yeah, but to apply that, try to take a look on the example, example 1 in section 2.5. Okay, that's for today. Tomorrow we will apply what we learned